begin today. You probably already noticed, actually, that we changed the way that the Wi-Fi works. So if you have any problems with the Wi-Fi, or if you're currently having problems with the Wi-Fi, we do have people available to help work out those kinks. So just raise your hand or flag somebody down so that we can get those issues sorted out. But you should be able to log in with your email address that you used to register for the class. And if you could, please remember to choose the reason why you're here from the drop-down box before you log in. If you didn't do it today, not a big deal, but in the future, if you could just remember to let us know the reason that you're here so that we can track that information. And I was also asked to pass along, we are not tracking anything you do on the internet. We're not looking at the websites that you're looking at, stuff like that. So don't worry about us snooping around. That is not the purpose of the Wi-Fi. We're basically just trying to get an idea of how many people are here and why they're here. So that's sort of what we're using that for. But yeah, if you have any problems, if you have any questions, let us know so that we can get those sorted out. For the most part, I think it's been working pretty well. Again, just as a reminder, we do have spring break coming up week after next. So next week we'll be here. Spring break, we're not officially going to have class, but there are going to be some sessions during spring break for people who are still working on stuff to just come in. It'll be like office hours, come in and get help. In fact, I myself will be here probably around the same time, Tuesdays and Thursdays at 5:30. I don't know if I'm going to stay till 8:30, but I will definitely be here on those days, and there will probably be other times during spring break that we have some office hours as well. So I will give more information about that next week too. Any other questions before we begin today? All right, cool. So today we're going to talk about linked lists. That is the main topic of today's session, is linked lists. We're also going to see, hopefully, recursion pop up again today as well. So let's talk about linked lists. Who can describe what a linked list is? Somebody tell me what a linked list is? Oh yeah, if you don't mind hitting the lights, that'd be great. Thank you. Can you guys hear me okay too, by the way? Do I need to turn it up? We're good? Okay, cool. Yeah, who can tell me what a linked list is? What's a linked list? Yeah. Cool, awesome. So you answered both of those first two questions for me. That's great. It's an array is stored in one continuous chunk of memory. A linked list is not. A linked list could be all over the place. And to get around that, what seems like a disadvantage, the way that we get around that is by including a pointer to the next thing in the list, right? So that we always know how to find it. Hence the name linked list. So I'm glad you brought up arrays, because I wanted to talk about that actually. Spend a few minutes discussing what's the difference between a linked list and an array. Can somebody give me some differences? Yeah. Yeah, once I've created an array, that length is set in stone. So if I run out of space with an array, what do I have to do? I have to create a new one and then copy everything over, right? We actually saw an example that did something very similar to that a week or two back, right? With strings, I think maybe is what we did that with, or it could have been something different. But we did a similar example to that. So array sizes are constant. Once I create an array, that's it. With a linked list, that's not true, right? With a linked list, if I run out of space, or is there really any such concept of running out of space? Not really. Not really. I can just tack on new nodes at the end of the list whenever I want to, right? Any other differences you can think of between arrays and linked lists? What if I want to get something out? So creating them is one thing. What if I want to get stuff out? So I've got a list and I've got an array. Yeah. Mm-hmm. Yeah. So that might be a potential disadvantage of a linked list. If with an array, I can just go directly to the position that I'm interested in and see what's there, right? We have these indexes that take us directly to that spot, and we can just immediately look at whatever's there, or we can change whatever's there too, using that same mechanism, right? With a linked list, I don't have that ability. at least not directly. With a linked list, if I'm looking for a value, I start at the beginning, right? And I have to go through every item until I find the one that I want. So that's going to take longer, right? That's going to take longer in general than an array. In fact, we've got a term that we can use to discuss how long these things take. Does anybody remember what I'm talking about? Big O. Big O. So if I'm looking up a value in an array, what's the big O of that? Constant. It is. It's constant time. How do we know it's constant? Because it's going to take the same amount of time for each one, right? I just have to know the address. As long as I know the address, the index that I'm looking for, I just go directly to that address and I pull the information back out. What's the big O of pulling an element out of a linked list going to be? N, what does N stand for? The number of things in the linked list. So big O, that's actually the worst case, right? So that's saying if I'm looking for a value, the worst possible place for it to be in the linked list is where? The very end. It's not always going to be at the very end, though. So we could talk about average case as well. What's the average case of looking up a value going to be for a linked list? Any ideas? N over 2, because on average I expect it to be roughly in the middle. Right? Maybe it'll be closer to the front one time, but closer to the end the other time, but those average out to be roughly in the middle, right? That's the average case. Yeah, we can also talk about inserting stuff. We can also talk about inserting stuff into arrays and linked lists. In fact, with arrays, it's pretty straightforward. We already kind of talked about that. I just say the address that I want and what value I want to go into that address. So what's the big O of inserting stuff into an array? Any ideas? Constant. It's also constant, right? Just like pulling stuff out is constant time, putting stuff into an array is also constant time. What about a linked list? This is a little trickier. If I want to add stuff to a linked list, it kind of depends on how we do it. There's not just one way of adding things to a linked list, right? What are my options when it comes to adding things to a linked list? Do you remember from the prep work? Yeah. I can put it at the beginning, and the big O of that would then be, I know you just said it, but for people who didn't hear you, what would the big O of that be if I just always put the node at the very front? That would be constant, right? That's easy. What if I put it at the end instead? What would the big O of that be? N, where N is the number of nodes again, right? Or there's a third alternative, which we may or may not have time to get to today. I kind of hope that we do, which is maybe I can store the list in sorted order so that everything in the list is always sorted, right? That has some advantages. What are some potential advantages of storing things in sorted order? Do you see how that would maybe make certain operations easier for us? I can search faster, right? If everything's sorted, then as soon as I find a value that's larger than what I'm looking for, I know it's not in there, so I can stop, right? I don't have to go through everything. I can stop once I get past what I'm looking for. And insertion-wise, right, does that make it easier or harder if I keep things in sorted order? Easier? So I'm not going to go all the way to the end most of the time, right? It's usually going to be in the middle somewhere. If I'm storing things in sorted order, more often than not, it's probably going to be in the middle somewhere. So it's slower than just putting everything on the front. Almost anything's going to be slower than that. That's the fastest way that we can add stuff to a linked list. But it's definitely faster than always adding things at the end, right? It's definitely faster than that. So it's kind of somewhere in between. Good. Any other questions about linked lists before or comments about, well, actually, we didn't answer this last one. When should you choose a linked list over an array? Any ideas? When's a good time to choose a linked list versus an array? Yeah. Yeah, if I know how much stuff I have, an array is pretty good. Array is pretty good for that, right? If I don't know how many items I have, a linked list is pretty good for that, because a linked list can be very flexible, very much flexible. But the downside then of using that linked list is it's probably going to take me a little bit longer to put stuff in and get stuff back out compared to an array, right? Good. Any questions about linked lists before we try some exercises? try some coding exercises. Alrighty, so we're going to start with the basics, the basics. In fact, some of this might be, stuff that you've already done over the course of the prep work today. But I think it's always good to reinforce these concepts. So, for starters, before we can do anything, oops, I did the wrong thing, sorry. 1 second here. I hit the wrong button. All right. Before we can do anything, we have to define a structure that can be used for our linked list, right? What are these structures typically called? Nodes. They're called nodes. So we need to have some sort of node structure. I'm sure you saw one if you did any of the prep work this week. You probably saw some sort of node structure. What does this mean, singly linked lists? What's the alternative to a singly linked list? Doubly linked list. So what's the difference? Yeah, so a doubly linked list can go in, I can travel in both directions, whereas a singly linked list is kind of like a one-way street, right? I can only go from the beginning to the end. I can't go backwards, I can only go forwards. Do you see that there are benefits and disadvantages to that? If I don't need to go backwards ever, then that's not a big deal. Right? I don't have to worry about that too much. But going backwards is sometimes useful, so. In this case, we're going to stick with singly linked lists. For the studio today, you're actually going to get a chance to play around with doubly linked lists. We might talk about that a little bit later. So the first thing that I want to do, and we'll do this first one together, is to define a structure that can create singly linked lists of integers. So why don't we go ahead and tackle that? I'm going to switch over to my IDE, and I need to create a file to work with. I don't have anything for this yet. So Module 5, I don't even have a lectures folder yet. Let me create that real quick. New folder. And then I'm going to create a file for us to use. I'll call it listpractice.c. You, of course, are free to call it whatever you would like. And we'll probably need the usual suspects in terms of what we need to include, right? So standard I/O is almost always a given. CS50, almost always a given. If I can spell include right. And we'll create a main method for us to use at some point in time. We might not need it right away. The first question said define a structure that allows us to create a singly linked list of that contains integers. So who's got some suggestions for me on what I need to type in to make that happen? How are we going to create this? I'm sorry? Type definition. So I need a type def. What am I going to type next? Structs. And then what comes next? The name. So we call it node. Right? Okay, what next? Curly braces, and now I have to decide what goes inside of this structure. So what are the pieces that I'm going to need to be part of this structure? What do I need in order for this linked list to work? I want a singly linked list of integers. That's really all we need to know to define this structure. So what do I need to put in here? I need to put in an int, so this is, you might hear this referred to as the payload. This is what the linked list contains, right? So an integer, call it, I don't know, none. I don't know. And then I also need what? I need a pointer to the next item in the list. So what type is that going to be? Node pointer. I need that star in there, right? You need to make sure to have that star in there to indicate that it's a node pointer. And we'll call that next. Okay? And what else do I need then to finish this structure off? Don't I need to put struct in front of node star? Sure. Like that. Do I need anything else to finish this off? I'm sorry? I heard 3 people at least. Name and a semicolon. So I have the name up here, right? Is that where that goes? I need it again. Yeah, so Oops, oh, great. I accidentally deleted it, sorry. There we go. All right, are we good? Are we good? Anybody have any issues? Anybody have any questions with this? Are we good? Okay. So in main, I want to create a linked list, but I want my linked list to be empty. I want it to have nothing in it at first. So how do I do that? How am I going to create an empty linked list here? A linked list that has absolutely nothing. Yeah. So I want to create a list that has nothing, like absolutely, positively nothing. So when I'm malloking memory, that's something, right? I'm glad you brought that up. We do need to have talk about malloc at some point today. But right now, I just want to create a list that has absolutely nothing. Yeah. Set it equal to null, right? Just set it equal to null. So, okay. Node. What's a good name for this node? Head, maybe? Equals null. Oops, forgot the equals. So now we've got this node that we're calling head that is absolutely empty. It's an empty list, nothing in it. Yes? Yes, it is. Thank you very much. The compiler would have been happy to remind me about that eventually. All right. So we've got a good start. Now let's take a look at what else I want us to take care of. So we want to define a function that takes an integer value and creates a new node at the end of a list containing that value. So we'll call this function append, right? We'll call this function append. Let's think about, before we write the function, let's think about how we want it to work. How do we want this function to work? What does an append function need in order to do its job? What all does it need to know in order to do its job? Or maybe another way of asking this is, if I want to call this append function, right? Eventually I want to call this append function. What do I need to give it here? How do I want to treat this? What values do I want to pass into append to make it work? Yeah. So it needs some sort of a value, right? So I can just make one up. I'll use 7. Do I need anything else? Do I need anything else? I need the list that I'm appending to, right? So I need to give it the list that I'm appending to. There's alternative ways of going about this. I could have made this a global variable, but you know kind of how I feel about global variables, right? I could have made this a global variable, which would eliminate the need to do this, but I like this way better. So the value that we want to create, and then the list that we want to add it to. All right, so now we're going to go and create this function. What should the return type of this function be? Okay, void is good. There's alternatives to void that might be helpful here. It might be helpful. Sometimes instead of using void, and I'm not saying we have to do this right now, I'm just kind of throwing it out there as a suggestion. Sometimes instead of using void, it can be nice to use maybe give some sort of indication about whether the function worked or not. So we can maybe use a Boolean to say true if I successfully created the node and added it onto the end of the list, and false otherwise, right? I'm not saying we have to do that here. I just thought I would mention that real quick. So append is the name, and now we have to define our inputs. So the first type is just int, right? Call it value. The second, what's the type of the second input? It's a node. Yeah, so actually, do we like this type here, node? No? I heard somebody say no. Person who said no, what do you think it should be? Node star. So node pointer. I kind of like that too, actually. Kind of like that too. Which would mean this is also going to be node star, and we'll call it this list. Okay. So we are now ready to start defining what we want this function to do. Before, so I'm going to actually ask you to do this as an exercise, but we can write up some pseudocode, right? We're going to have some pseudocode for this. We do have one particular thing that I think is maybe easy to overlook here that we need to check for. Does anybody know what I'm talking about? For the most part, adding a node to the list isn't that bad. Just find the end of the list and add it on. But there's one particular situation where finding the end of the list and adding a node is going to be a little different. Yeah? Do we have to check if the memory is available? So we do need to worry about memory. That is something that is our concern. I think we're going to be requesting the memory ourselves, though, for the nodes that we're adding. We have to make sure that there's something in the list. So in other words, how does this behave the first time, right? The first time I add a node, my list is empty. It's absolutely empty. It's null. So we need to accommodate that, right? The way that we treat an empty list is going to be a little bit different than the way that we treat a list that has stuff in it already. Do you see that? So what am I going to use to, what kind of structure do I need to choose between those two conditions? We can use an if statement, right? If the list is empty, right? Then what? Create the node. Add to list. I'm going to put a question mark there. Else create the node. And then what do I have to do? Let's assume that the list has stuff in it. What do I have to do before I can add this guy in? I have to find the end. How do I know when I've hit the end of my list? The pointer is not pointing to anything, right? The very last pointer is not going to be pointing to anything. So find the end of the list. We'll put here, next is null, just to kind of remind ourselves, and then add node. Now, I've coded this pseudocode up in a certain way, but it's not the best. The way I've done it is actually not the best way to go about it. Does anybody see a way we can do things a little bit more efficiently? Yeah. Can we create the node before the if? I like that idea a lot. If I ever see something duplicated, right, my brain is very much trained to say, hey, can I get rid of that duplication? Here you see I'm creating a node in both the if and the else. So really, creating the node doesn't depend on whether or not the list is empty. I'm going to create the node always, no matter what. So maybe creating the node, maybe I can just get that out of the way first. Since I know I'm always going to need to do it, I'll just do that first, and that gives me fewer stuff to do inside of my if else statement. Does that make sense? It's a more efficient approach. So the hard part here, I think, is going to be this. Find the end of the list. Find the end of the list might be a little tricky. If you've done the prep work for this week, maybe a little easier on you. You can refer back to those examples. But I'm going to pause and give you a few minutes, 5 or 10 minutes, to try this out. And then once you're finished, maybe take a look at this next one. Define a function that can print the contents of a list. This is going to be useful because we don't really know if our first function is going to work unless we can see the actual contents of our list, right? So take a look at this one if you finish up this first one. I'll be around. I'm sure we've got mentors around as well if you have any questions or get stuck. And we'll go over the answer in just a few minutes. What happens? Alrighty. Let's see what we can do about this problem. So the first thing it says we need to do is to create a node. How are we going to do that? What do we have to do to create our node? What do we have to do to create a node? Yeah, we have to malloc. We have to malloc. So I need to create this node. I'll call it node, right? Malloc. What am I going to put inside of malloc? Size of node. We okay with this? Node star, good, good. All right, so we have our new node. Now I need to get the information into it, right? Oh yeah, thank you. New is a poor choice. New is a poor choice of name. Thank you. So I've got this new node now. Now I need to get the information into it. So I need to put the value into that node that I created. How am I going to do that? I have a node pointer. How do I access the things inside of this node since I have a node pointer? What am I going to say? The arrow. I have to use the arrow. Good. So new node arrow. What did I call it? Num equals value. That should put the value in there. I've got one more I have to do as well, right? New node next. What should the next be? What should the next be? Where's this node going to end up eventually? It's going to end up at the very end. So what should the next value be for the node that's on the very end? It should be null. So let's just set it to null. All right, cool. So we've created our node. Now I can take a look at this next part. If the list is empty, how do I check to see if the list is empty? If list equals null, if the list is empty, that will be null, right? That's how we defined it up here, anyhow. Right? I need to add this node to the list. How am I going to do that? How do I add this node to the list? So we have an empty list and a node that I just created, and now I want to add this node to that empty list. How do I do it? How do I do that? Yeah, in the back. List equals new node. Is this okay? How do we feel about this? Let's see. I'm sorry? List next equals new node. Does this have a next? It's null, right? It's empty. No. We already did a malloc. Yeah, we did a malloc. So these are pointers, right? These are pointers. I'm just saying take this pointer that's now pointing to nothing and make it point to this thing instead. Is that what I'm saying? Is that what I'm saying? Tell you what. I'm just going to put a little comment here that we're unsure about this. And we're just going to try it later. We're going to move on. We're going to try it later. Maybe we don't know for sure whether it's going to work or not. Best thing we can do is just try it later. Let's code up the rest, and then we'll come back and try this later and see what happens. So otherwise, I need to find the end of the list. So here, I'm going to say else, set up some brackets. How am I going to find the end of this list? What am I going to do? What's the procedure here for finding the end of this list? I need to find the node in the list that has a next value of null. This value here, this node pointer, is always pointing to the first item in the list, right? The very first item in the list. So there's probably going to be stuff after that, most of the time. So how do I go through the list until I find the end? What do I need to make that happen? Yeah. A new node pointer. I like this idea. So node pointer, we'll call it n. I don't know. And what am I going to set this node pointer to? the first node, which in our function is what? List. So we'll set it to list. And now what am I going to do? How do I find the end? A while loop. I like a while loop here. I like a while loop here. I know people in general seem to be favoring for loops, I've noticed. They really like for loops. And I like for loops too. But for this purpose, I think a while loop works really well. Yeah? Call it what? Crawler? Sure. Absolutely. We sure can. So I am going to keep, so I have this while loop here. When am I going to stop? What's my end condition? While what? Oh, I already have brackets. What am I doing? While what? So next is not equal to null. While what next is not equal to null? Ah, shoot. Crawler, yeah, there we go. Crawler next is not equal to null. What do we want to do then? What do we want to do in this case? What are we going to do inside this loop? We're going to need to move to the next node, right? We need to move over. We're going to use crawler to keep track of our position. So how do we tell crawler that we're done with this node and we want to go to the next one? What do we do? I need to change the value of crawler. What am I going to change it to? Crawler arrow. Oops, wrong arrow. Next. So take whatever the current next value is of crawler and then make that now what crawler is pointing to, right? It's all pointers here, so we're just telling crawler to point at the next node in the list. That's what this is saying. Do I need anything else in this loop? Do I need to re-explain? This is a very important piece, so I want to make sure. Okay, so once we've done that, once this loop is over, I know that I'm where? I know that I'm at the end. So now I just have to add the node, right? I just have to add the node. So where is that node going to go? How am I going to add that node to the end of this list? Yeah. Crawler next. It's a new node. So when this loop is over, we know crawler's at the very end, which means I want to set the next node to be that new node that we just created. Does that make sense? Any questions about this? Any questions about this process? I think this is good. Well, with the exception of this part that we're unsure of, that we're going to test in a little bit. I'm going to test this out in just a second. Let me get rid of my code here. Okay, so we've got this append function. We think that it works. But before we can test it, we kind of have to print out, we need a way of displaying the contents of the list so that we can make sure that it works. So maybe before we test this one, we should also create that second function, the print function. We can do that together. I think that one will go together a little bit faster. I want to create a function called print list, right? And what am I going to provide as inputs to this? What am I going to provide as an input? I want to print out a list, so what do I need to give it to do its job? I need to give it a list, so that'll be head, right? And I shouldn't need to give it anything else. So now let's talk about what this print list function is going to look like. Always start with the return type, so what's that going to be? Void print list. We know that the input is going to be a list. We stated that, so node pointer list. And now what mechanism are we going to use to traverse this list? We're going to use this same kind of structure, right? Use the same kind of structure. Okay? Not a problem. We do still need to be a little bit careful. What if I give you an empty list? That would be kind of mean of me, but I could do it, right? I could give you an empty list and say, here, print out this empty list. So we still need to be a little bit careful. I think it would be good practice to check to see if the list is empty or not before we try to do anything. So I'm gonna borrow some code. I mean, why not? We have a feeling that it kind of works. So if the list is empty, maybe I can just say empty list. Just tell you that it's empty, right? Just say it. Otherwise, there's no reason to reinvent the wheel here. We've got this code that we think is going to go through and visit each node in the list. So why don't we borrow it and tailor it to suit our needs? There's some stuff in here that we need. There's some stuff in here that we don't need. There's some stuff that we're going to need to add. What's something that we don't need? There's some extra stuff in here that we don't need. We don't need this line. That's adding a new node. We don't need that. New node doesn't exist anyway, so we don't need that line. We do need to add something that's going to print out the contents of the list. Where should that go? Where should I print stuff out? Inside the while loop. Good. So printf. These are integers we're talking about, right? So I'll say I. And then how do I get the value that I want to print out? What's the value that I'm trying to print out here? Crawler, arrow, I think I called it num, right? This should print out the value that's in the node and then move on to the next one, right? Is this going to hit every node in the list? It's good to get in the habit of thinking about edge cases. I think you should always pay attention to stuff that's going to happen at the very beginning and the very end, because those can oftentimes be different. So will this print out the first node in the list successfully? Yes. Will it print out the last node in the list successfully? No. Why not? Because we're checking to see if crawler next is equal to null. And if it is, then we're going to stop. So we're not going to print out the last node in the list. So how do I fix that problem? Add another printf after? That's one solution, sure. I could put another printf down here. I think there's maybe a slightly more efficient way to go about it. Does anybody have any alternative ideas? Yeah. Yeah, we can just take the next off, right? Because if crawler is null, what does that imply? If crawler somehow equals null again, what does that mean? I've gone off the edge, right? I've gone off the end of the list. That's what it means when crawler hits null, right? So if I see that crawler is equal null, I've gone off the edge of the list. Until that point, keep going. Just keep doing what you're doing. Does that make sense? All right, let's test this out. Actually, there's one thing that I always forget when I do these exercises that I need. Prototypes, yes. I remember this time, though, kind of. So I will quickly add these prototypes up here at the top. And then we can try this out. Oh, thank you very much. Should we also free? Absolutely. Absolutely. What happens if we don't free? What's that called? Memory leak. So right now this code is leaky. So how do we, so freeing is easy. It's just free and then the thing that we want to free. But how do we actually, we need to be a little careful here. I need to free what exactly? I'm freeing the list as a whole, or? Well, I don't want to free until I know I'm finished, right? I don't want to free until I know that I'm done with everything, right? So I need to free what? I actually need to free every single node that I created, right? I can't just free the first one. I can't just free the last one. I need to free all of them. I need to free all of those nodes. So how am I going to visit each node and free it? A while loop, right? We're going to use a while loop. In fact, we'll use a similar construct that we did before, right? Maybe this one. And I'll put it where? When do I know I'm absolutely finished with my list? At the end of main. That's a great place for it. At the end of main. So here I'll stick this while loop one final time. Sorry, the indentation's bugging me. All right. And now I just want to free everything, right? I just want to free everything. But I have to be a little bit careful, don't I? I have to be a little bit careful. What happens, so it's tempting, and it seems easy to just say free crawler, right? Oh, I deleted something important. It seems very tempting to just come up here and say free crawler. But what's the problem if I do that? Well, it doesn't exist in main. That's one problem, but I can fix that problem. Instead of saying node crawler equals list, what do I want to set crawler to at the beginning? I don't have this. What am I calling my list? Head. Okay, so that's one issue. There's another problem, though. Anybody see it? Anybody see what the other problem is? I'm freeing crawler, and then I'm saying move on to the next thing. Do you see that? But I can't, because I don't have that information anymore. It's gone. I freed it. So how do I fix this problem? I'm sorry? Switch the two lines. So let's do that and think about, whoops. Think about what that, so I'm saying move on to the next one and then free. So I'm actually skipping, I think, at least one node if I do this, but I still have the same problem. I free it and then I try to go to the next one. Well, I can't do that. It doesn't exist anymore. It doesn't exist anymore, right? How do I fix this problem? This is a little tricky. I need another pointer. Yeah, I like that idea. I like that idea. I need another pointer. This is, to me, this kind of has a feeling as similar, not exactly the same, but it feels a little bit like that swapping problem, where I can't just swap the two variables because I'm going to erase something and before I'm done with it. This is kind of a similar feeling to me. So how did I fix that with the swap? I created a temporary thing that I could then use, right? So maybe that'll help us here as well. Before we free crawler, maybe I'll create a temporary node pointer. And then what do I want this value to be? Crawler next. So remember what the next thing is, right? And then down here, I can't use this anymore because that doesn't exist, but I can use my temp. Does that make sense? So remember what the next node is, get rid of this node, and then use that temporary thing to update where we are. Does that make sense? Does that make sense? All right. We have written a lot of code. We haven't tested any of it yet. That makes me nervous. So I want to test this code. So let's try it out. Let's see what mistakes were made. Hopefully none, but I always get suspicious if it works on the first try. All right, make list practice. It compiled list practice. So what am I expecting to see when I run this? What am I expecting to see? 7. I only have one node, right? The number 7. That's it. That's all I'm expecting to see. So if I run this, I hope to see the number 7. And instead I see empty list. Shoot. Shoot. Well, so good news, bad news. Good news is our print list seems to be working. Bad news is we didn't get the list that we wanted. We didn't get the list that we wanted. So what's the problem? What do you think the issue is? What do you think the problem is? Yeah. Yeah, it's probably this thing we were unsure about, this initial case, is the problem. And I knew this was going to be a tricky piece. I knew this was going to be a little tricky. So list is a node pointer. New node is also a node pointer. But so it seems like this should be okay. But what's the problem? What's the problem? This kind of goes back to passing by reference versus passing by value to some extent, right? When I pass things into a function, do I actually get that thing? I get a copy of it, right? So here, when I say list equals new node, I'm changing the copy of that pointer, which means it's going to go away at the end of the function. That's what we're seeing. I pass in a copy of the pointer to the front of the list, and then I tried to change it. That change goes away as soon as the function's over. What do I really want to do? I see somebody in the back. All right, so the question was this. Do we want to use the ampersand? List equals ampersand new node. So what does ampersand do again? It gives you the address? You got one of two options, right? It either gives you the address of something or it gives you something from an address. Which one is it? Address of. So it's going to give me the address of this thing. Is that what we want? Is that what we want? We want the actual value. We want the actual value. So how do we do that? Star, right? So I want to get the actual value here, and I want to store that as the actual value of this. So I'm not quite done. What do I need to do to finish this off? I can't change this pointer, right? We've already discussed. I can't change list directly. I can't say list equals anything. It's never going to work. It's never going to work. I can't change the actual value itself. But I can change whatever that thing is pointing to, right? I can change that. How do I do that? How do I get the thing that it's pointing to? Star. The value that this is pointing to, I want to be set to the value that this is pointing to. Does that make sense? Maybe? I haven't proven that it'll work yet, so we should definitely try it and make sure that it does. Maybe it doesn't. Let's try it. Segmentation fault, awesome. Cool. Nice. That does not work. Clearly. Well, did I paint us into a corner? That's certainly possible. You wonder if when we free crawler, we need to have crawler equal to temp before we free it. But that would be moving crawler to the next node and then freeing the next node, right? See that? Yeah. The issue, perhaps, actually maybe more than perhaps, is this guy. I'm actually kind of regretting this decision a little bit. Set this equal to null at first. Just a little bit. So I'll tell you what. Why don't we malloc a new node here instead, as was suggested. I don't remember who suggested to do this originally, but whoever that was, thank you. Let's try that now. Of course, that means I do have to create a node here as well, right? So I have to give this some initial value. Head num equals 2, head next equals 1. I think this should potentially fix our problem. If anything else, it eliminates the need to do this entirely. I don't have to do this anymore at all now, right? So this code was kind of a bust. Yeah, of course. I'm sorry. Let me, sorry. I just created a new node here. Instead of setting this to be empty, I just created a new node instead. Yeah. Kind of bothers me. I feel like that should have worked, but I want to keep things moving along, so. All right, let's try this again. So now I actually have two things, right? I have the 2 and the 7. So I should hopefully see 2 things. All right, cool. Much better. Much better. So a valiant effort, I think, to try and make this work. It didn't quite happen, unfortunately. And I guess I kind of understand why that was problematic, since that's null. That was a poor decision on my part. Sorry about that. But we've figured out a workaround, so that's good. And our code seems to be working. That's the other good news, right? I see the 7 on the end. So if I really want to test this, I can add more stuff to it, right? Let's do that next. Let's add some more stuff and make sure, and run it again and make sure that it still works. Right? We really want to test it out. I should see those values appear at the end, right? Cool. Everything seems to be working. Any questions about what we've done so far? We've still got time left. Yeah, question. Don't we have to free head? Are we currently freeing head or not? What do you guys think? Yes, we are. How do we know that that's in fact happening? The first thing the crawler gets set to is head. So that's going to be the first thing that we free. Yes. I'm glad you're thinking about that, though, because we definitely do need to free head, and it's better to be cautious about that than to miss something. Is there another question I saw somewhere? Yes. Can you repeat that for me? Sorry. Instead of creating 10, so we don't want this? Like this, crawler. Sure. I thought, did we try this before? This, what do you guys think? Well, it's not necessarily head that I'm worried about. I'm freeing crawler and then saying crawler equals crawler.next. Well, this has already been freed. I freed it the last time around. Do you see that? So I'm trying to reference something that I've already given back. I can't do that. Do you see? You're saying crawler equals crawler.next, free crawler, right? And then crawler equals crawler.next. Well, we just freed this. It's gone. It has no next. That's how we had it the first go around. Right. Well, so this suffers from the same issue, right? This is gone. I can't get the next out of it. It's gone. Yeah. Any other questions before we still have some time left, so I would like to try at least one or two more things. Yes. So the question was, can I explain why we're not freeing the memory allocated in the append function? Are we not freeing the memory allocated in the append function? Can somebody help me out here? Yeah. Mm-hmm. Right. So if I'm not freeing this, so this is freeing every node in the list, right? That's what we've stated. So if I'm not freeing then this memory allocation, then what memory allocation is this freeing? What other memory allocations could that be freeing? Well, we've only allocated memory in two places. We've allocated it here. That's the first node. That's one node, exactly one node. We've also allocated it here. This could be many nodes because we're going to call this function many times, right? So what is this freeing then? It's definitely freeing the first node, but it's also freeing every node thereafter. So it actually is freeing this. It actually is freeing the memory from that malloc. Do you see why? Do you see why? These nodes are getting added to the list that begins with head, right? So if I free every node in head, then I am freeing every node that was created as a result of this function. Does that make sense? Any other questions? Yes, in the back. You just put free crawler at the end? So, or would that be equivalent to free head? So, same thing? No? You ran through Valgrind and it worked? I'm a little dubious. I'm not trying to call you a liar, but I'm a little dubious. A little dubious. There should be a corresponding free for every malloc, right? If we just free the one thing, then that would be one single free call for potentially multiple malloc calls. So that's why I feel a little off about that. But I've been wrong before. I've been wrong earlier today, 10 minutes ago, so I could be wrong now too, I suppose. Any other questions? Any other questions? Okay. I've got tons of these. Somehow I'm destroying my slides in the process. I've got tons of these exercises. We don't have time to do all of them, unfortunately, but we can try these next. Define a function that returns the length of this list. So how long is this? And then define a function that computes the sum of all the values in the list. Why don't you take another 5-ish to 10-ish minutes, and we'll do at least one more of these before we wrap it up. I'll be around if you have any questions. Okay, these actually have very similar solutions, if you may have noticed. So I definitely want to do at least one of these. Maybe I'll do the length. Let's do the length. Let's do the length one. I didn't give you any help. I didn't give you any assistance or anything like that. I just said, go do this thing. So that was a little mean of me. But anyway, what do we need? What do we need to make this happen? I need to create a function that's going to take the length of a list. So where do I begin? Yeah. Yeah, so actually, I think we should keep it separate. Print list works beautifully. The suggestion was, can we go to the print list and just add them up? I think we can definitely use this as a basis for our function. Why not? It works beautifully. So yes, let's use this as a basis for our function. So I need to create a new function. What's the return type going to be? Int. Length will be an integer. I'll call it length. What's the input going to be? A list. So it'll be a node pointer list, right? And now I stole this code directly from the printer, right? Instead of printing, what do I want to do instead? What do I want to do instead? I want to count. So I need, if I want to count, I need a counter, right? I need a counter of some sort. That's easy to do. Int count equals what? 0. And then inside the loop, I just need to count up. So I'll say count plus plus. And then at the very end, what do I need to do? Return count. That's not so bad, right? That's not so bad. Okay, let's test it. Let's test it out. I need the prototype, of course. I need the prototype up here. I need to call this. So int L equals length of head. And then I can print that out. Printf length I. Make this practice. Length of 4. It works. It worked. I know I went a little quick, so somebody please tell me what questions you have. Sorry I went so fast. Question? Twice as long. So start from the beginning. Uh-huh. Sure. You're doing counts and print all in one shot, is that right? I mean, I could easily print out the elements while I'm in this loop, right? If I wanted to, I could just say printf and then print out the contents of the list all in one go. So that would be okay if that's something that you wanted to do. I'm not sure if that answers your question. Kind of? Yeah. I think it's good to keep them separate, though, personally. A function should have a well-defined behavior. This function is called length. I wanted to do one thing, which is figure out what the length is, right? I have another function for printing that I can use if I want to print. I think having those clearly defined boundaries is a good thing, right? Any other questions? I've got one more thing I want to do with you guys before I let you go, which is I want to redo this length function, but I want to do a little bit differently. I want to use recursion to make this happen. I know, I'm sorry. But we're going to do it together. It'll be okay. I promise. I promise. So let's do it. The function definition is going to be basically the same. Mostly because I want it to be basically the same. I do need to change the name at least, so I'll call it length R to indicate that it's the recursive version. Okay? what do I need for successful recursion? What are the things that I'm looking for successful recursion? I need a base case. And the problem has to get smaller. I have to get closer and closer to the base case. Those are the things that I need for successful recursion, right? So what's my base case here? My base case is when I stop. When do I stop? When my thing is null, right? In fact, we can use this as an example, when crawler is null. Or in this case, we don't have crawler, we have list, right? So if list equals null, I have to give a length here. If list equals null, how long is my list? How long is it? 0. 0. So return 0. Okay. Cool. Else. This is going to be my recursive step, right? So this is the trickiest part. But let's think about it for a second. Let me use the list that we already have as an example. I have this list. I know the length is 4. That's easy to see. So I say, take the length of this list. I look at this thing that I currently have. How long is just this piece? 1. 1. But then I also need to take the length of the rest of this, right? So if I want to take the length of the entire list, right? I want to take the length of all of this. Couldn't I say that the length of this whole list is the same as 1 plus the length of whatever comes next? You see where I'm going with this? So count the element that I'm currently on and add that to the length of whatever's after it. Does that make sense? So how do I say that in code? How do I say that? Return 1 plus, how do I take the length of the list? Length r. And then what am I taking the length of? List next. Does that make sense? So I need to find the recursive substructure here, right? If I have this whole list with 4 elements, I'm looking at the first element in the list. I can say that the length is the length of this first element, which is just 1, right? The length of one element is 1, plus the length of the stuff that comes after it, right? So I say 1 plus the length of whatever comes after this. That's exactly what this line of code is saying too. Return 1. This 1 represents this guy right here, the one element that we have, right? Plus the length of whatever comes after it, where whatever comes after that is list.next, right? You can actually think of this as being a sublist, right? It's a subset of the entire list. So I can take the length of that subset, right? And then I can take the length of this subset. I can take the length of this subset. And then eventually I'm going to go off the edge. I'm going to say, oh, I don't have anything else. I hit the end, right? And the length of that is nothing, 0. Okay? Let's try it out. Let's try it out. So instead of using length, I'm going to just stick an R on the end. I think I need a prototype too. So let me put that in there. And then we can try it out. And I hope to get the same answer that I had last time. Perfect. Perfect. It worked. If you did the sum version, right, you should be able to do a recursive version of the sum. Actually, you could do a recursive version of almost any of these functions. I think that would be good practice. If you haven't gathered already, you might see recursion somewhere in your near future, perhaps on a problem set. So I'm kind of encouraging you to think along those lines and get some more practice doing recursive stuff. Are there any more questions for me right now before we break? Yes? The append, yes, right here. Returning a node. I mean, you could certainly return a node, but then you'd still have to add it to the end of the list at some point, right? That would work for the first node. What about the next one, and the next one, and the next one, and the next one? I don't disagree with you. That would work beautifully. That would work beautifully. But what about the ones after that? Are what I'm a little worried about. Because you know, the name is append, which to me means that when it's done, that node is going to be on the end of the list. That's what that name implies to me. If it's doing something different, that's not a bad thing. I just don't think I should call it append. Maybe I'm misunderstanding the question. I'm not sure, what node exactly am I returning? The new node that's been created? The new node that's being created, is that what I'm returning as the output? Because if so, then that new node still needs to get added at some point. Or if it's already being added as part of the function, then I'm not sure I see the usefulness of returning it necessarily. I'm sorry? It can return any of the nodes that you want. It depends on which node you're returning, right? It could return the first part of the list. It could return the new node. It could return any node in between. Yeah, I know I'm playing devil's advocate. That's kind of my job. I can come back and take a look at it. See what's going on. Any other questions that I can answer before we can I go back up to main? Absolutely. I'm going to post this code too, as I always do. Can't quite fit it all in. There we go. That's almost all of it. Trying to get it all on the screen. Can't quite fit it in. I'm going to post this, you know, like right now, ish. Any more questions for me? Yeah. Uh-huh. Yes, absolutely. That would also work. And actually, that might save us a little bit of effort. Yeah. Good. Okay, you have a studio to do today. It involves the getString function. As part of the prep work, they ran you through how the getString function works. If you haven't already, let me pull up the website real quick and just show you one thing here. If you haven't already looked at this one piece of the prep work, it's kind of down at the bottom, getString with lists. If you haven't already looked at this resource, you might want to take a look at that before you start today's studio. Even if you have already taken a look at it, you might want to have it open while you're working on today's studio, because today's studio is built on this resource. It basically starts where this resource leaves off and asks you to take it a few steps farther. So I would highly encourage you to take a look at this before you get started on today's studio. And I'm happy to answer any questions that you might have about any of this stuff. So I think that's it. I'm going to turn you guys loose. Thank you very much.